Okay, so the purpose of this video is to attempt to demonstrate how to find a derivative, or rather a rate of change at a particular point on a function. So suppose we had a function given by, I don't know, let's go with a sinusoidal function. So we'll go with sine of x. And now I'm going to adjust the zoom on my plot so that it's a trig zoom by going down to 7. And we'll take a look at that plot. So here you can see that we have a graph of sine of x, and it's going from about negative 2 pi, pretty close to negative 3 pi, all the way to positive 3 pi. Now, suppose I want to find the rate of change at a particular point, like maybe either here at the top or here right as it crosses through the x-axis. I can find the rate of change at one of those points by calculating what's called the derivative. So first I'll calculate it, then I'll show you what we're actually finding. So to do this, we press calc, which is above our trace button. So we'll do second function, trace to do calc. And we'll go down to 6, which is dy over dx, or delta y over delta x. And you may remember delta y over delta x as being y2 minus y1 over x2 minus x1. That's our slope formula. So slope and rate of change and all of these things are related. And we're going to calculate dy dx, which is just the derivative. So we'll calculate dy dx, and we can scroll over to a particular point using the arrows. Or, we happen to know that this first 0 occurs at pi, so I can just type in pi as my x value and hit enter. And it'll give me dy dx. It'll tell me that I'm dealing with a rate of change of 0.99999, though that's going to be a negative rate of change. So we can assume that that means that the slope there is at approximately 1. Now, negative 1. Now what we're actually finding is we're finding the slope of a line that's tangent to this. So let's go ahead and plot a tangent line here. Now I'm going to plot the tangent line with a slope of negative 1, and I know that its y-intercept is going to be positive pi. Now I did that just by calculating the y-intercept using the point pi and 0. But we'll go ahead and we'll see this line being graphed onto my function. So I don't know if you can see it in red. It's tougher to see if I tilt. So we can see in red, and I'll trace over, that slope that we calculated at that particular point is actually the slope of a line that runs tangent to the curve. And that would be the exact or instantaneous rate of change at that particular point would be the slope of this red line. So we can recall that the slope of our red line was negative 1, and that's because at that particular point of pi, we had a slope of negative 1. So let's try this for another function. I'm going to go ahead and reset my calculator. And I'm going to plot, I suppose, an exponential function. Let's go with 1.75 to the power x. And now I'm going to adjust my zoom to just being a standard zoom. And we should see we have a nice exponential function plotting itself up here. Now, suppose I was interested in the rate of change along this function at some particular point. Like maybe I was interested in finding the rate of change, I don't know, right here. That would mean I'm interested in finding the slope of a tangent that goes through only one point on the graph at that value of the cursor. Now I can just go ahead and draw that tangent, or I can use calc. So second function trace to bring up calc, and I'll go dy dx, so 6. Now my cursor is already at that point, so, I don't think I did that correctly. I'll just hit enter, and you'll see that my slope is 2.574666. So I now know the slope of the graph at that particular point, which means I know the rate of change. Now, obviously, what's happening is as I go up higher, and I'll just do a slope even higher. So instead of doing it at 2.72, I'll do it at 3. because the line is getting steeper, you can see that the slopes are getting steeper. So the previous one was 2.5, the next one's 2.9. We calculate another one. We'll calculate another slope at about, let's go 3.1. And you'll see it's getting even higher. So as we move to the right, so as our cursor moves here, our slope gets higher because our rate of change is becoming steeper. As we move to the left, the slope gets lower because our rate of change is getting slower. Now, the rate of change is that tangent line, so we can imagine it being that line that is just touching at one particular point. And as I go further and further down the graph, that's going to get to 0 because I'm going up against a horizontal asymptote and it's getting perfectly flat. Some functions will have negative rates of change, and that will affect the way that it looks on the graph. And you can calculate these by actually manually finding what's known as the derivative, or by using second function calc and 6 if you have a function already typed in. You can choose to find the derivative by scrolling across a particular function to any point, or by typing a particular value of interest, like, I don't know, 1. And then you'll read your slope as being dy dx, or the slope of this graph at the value of x equals 1 is equal to about 1, 0.979. And that's how we use our calculators to calculate the rate of change of all types of functions.